Welcome to this coding problem walkthrough. In this session, we'll be tackling LeetCode problem number 1540, titled Can Convert String in K Moves. This problem challenges us to determine whether one string can be transformed into another within a given number of moves. We'll explore the problem requirements, break it down step by step, and analyze the solution. Let's get started. In this problem, we are tasked with determining if we can convert one string, s, into another string, t, in exactly k moves. Both strings, s and t, are of the same length, and the operation we can perform involves incrementing any character in s by 1. For instance, if a character is a, it becomes b, and if it's z, it wraps around to a. The goal is to evaluate whether it's possible to transform s into t within the exact number of k operations, and return true if it is, or false otherwise. This problem involves analyzing the relationship between the characters in s and t, as well as the constraints on the number of moves allowed. The input includes strings s and t, both made up of lowercase English letters, and an integer k that specifies the number of moves. The output is a simple Boolean value indicating whether the transformation is achievable. Let's explore some examples to better understand how this works. For the first example, we have s equals input, t equals output, and k equals 9. To transform s into t, we can increment the characters as follows. First, increment s, 0, which is I, by 6 to get o. Next, increment s, 1, which is n, by 6 to get u. Finally, increment s, 4, which is t, by 1 to get u. If we add up all the increments, we have 6 plus 6 plus 1, which equals exactly 9 moves, matching the value of k. Since the transformation is achievable in the exact number of moves, the result is true. This demonstrates how the operation can be applied selectively on individual characters to achieve the required transformation. In the second example, the input is s equals abc, t equals bcd, and k equals 10. To transform s into t, we increment each character by 1 as follows. Increment s, 0, which is a, by 1 to get b, increment s, 1, which is b, by 1 to get c, and increment s, 2, which is c, by 1 to get d. The total number of moves required here is 1 plus 1 plus 1, which equals 3. However, since k is 10, there is no way to use exactly 10 moves while achieving the transformation, as the minimum required moves are only 3. Therefore, the output is false. This example highlights the importance of matching the exact number of moves specified by k. In the third example, we are given s equals ab, t equals bbcc, and k equals 4. To perform the transformation, we increment the characters as follows. Increment s, 0, which is a, by 1 to get b, increment s, 1, which is a, by 1 to get b, increment s, 2, which is b, by 1 to get c, and finally, increment s, 3, which is b, by 1 to also get c. The total number of moves here is 1 plus 1 plus 1 plus 1, which equals 4, matching the value of k. However, even though the total moves align with k, the transformation still fails because every character in s is only incremented once, which means we cannot make further adjustments if needed. As a result, it is impossible to achieve the transformation, and the output is false. This example shows that meeting the move count alone is not sufficient if the transformation itself is not feasible. The problem also includes constraints and edge cases to consider. For example, s and t will always have the same length, and both strings consist only of lowercase English letters. The integer k can be very large, up to 10 to the power of 9, which means we must design an efficient solution that works even for long strings with significant constraints. Edge cases to keep in mind include scenarios like when s equals t, in which case the result is true if k is at least 0, and when k is less than the minimum moves needed to transform s into t, where the result is false. Additionally, we must handle wraparound cases where a character near z in s needs to become a character near in t. These considerations ensure that the solution is robust and handles all possible inputs within the constraints provided. To tackle the problem of determining whether we can convert string s to string t in at most k moves, we considered two main approaches. First, the brute force approach involves directly simulating the transformation. For each character in s, we calculate how many increments are needed to match the corresponding character in t, summing these increments to ensure the total is within k. While this method is straightforward to implement, it becomes computationally expensive for longer strings. Specifically, it requires n squared time if we simulate every increment, as each character operation involves multiple iterations. On the other hand, the optimized frequency-based approach eliminates the need for direct simulation by focusing on the mathematical relationship between the characters. Here, the shift required to align S(i) with T(i) is calculated using the formula T(i) S(i) plus 26% 26. By counting the frequency of these shifts for values between 1 and 25, we can validate whether the transformation is possible within k moves. One key insight here is the cyclical nature of the alphabet, which makes this computation efficient and avoids redundancy. Now, let's break down the details of the optimized frequency-based approach further. If a shift x occurs frequency, x, times, the moves required for the jth occurrence of that shift can be expressed as x plus 26 asterisk, j1. This formula accounts for how larger shifts wrap around cyclically in the alphabet. For the transformation to be valid, the maximum move required for any shift must satisfy the condition x plus 26 asterisk, frequency, x, 1 equals k. This ensures that all occurrences of the shift can be completed within the given number of moves. The beauty of this approach lies in its efficiency. The time complexity is reduced to n, because we only make a single pass through the strings to compute shifts and their frequencies. Additionally, the space complexity is constant, as we only need an array of size 26 to store the frequency of shifts. While this method is more efficient, it does require a solid grasp of modular arithmetic and the behavior of cyclic shifts, which may make it slightly less intuitive than brute force for beginners. The optimized frequency-based approach was chosen because it strikes the best balance between efficiency and scalability. It processes the input strings in a single pass, avoiding the repeated computations of the brute force method. This makes it well suited for handling large inputs, such as when n approaches 100,000, as often seen in competitive programming scenarios. When comparing the two approaches, brute force is simpler conceptually but becomes highly inefficient as the string length increases, making it impractical for large-scale problems. In contrast, the optimized approach is significantly faster and uses less memory, though it requires a deeper understanding of cyclic shifts and frequency counting. Other alternatives, such as pre-computing shifts or introducing additional data structures, were considered but found to add unnecessary complexity without improving the time performance. Ultimately, by leveraging the cyclical nature of the alphabet and focusing on validating the maximum moves for each shift, the optimized approach delivers the clarity, efficiency, and scalability needed to handle this problem effectively. The problem asks us to determine whether we can convert one string, s, into another string, t, within a given number of moves, k. Each move allows us to increment a character in s by one step, and this increment is circular. For example, converting a to b takes one move, while converting z to a also takes one move because of the circular nature. However, converting it to c would require two moves. The key constraints to keep in mind are that the lengths of s and t must match, otherwise, conversion is immediately impossible. Additionally, the total number of moves used must not exceed k. Furthermore, the differences between each pair of characters dictate how many moves are needed, and we must ensure that no two increments of the same type happen at the same time. This introduces an interesting layer of complexity that we'll address in the algorithm steps. To solve this, we begin by validating the input. The first step is to check if the lengths of s and t are equal. If they're not, we can immediately return false because the conversion is impossible. Next, for each character pair, s, I, t, I, we calculate the circular difference, which tells us how many moves are needed to convert s, I, to t, I. This difference is calculated using the formula, ord t, I, ord s, I, plus 26% 26. The addition of 26 ensures that we always get a non-negative value, even when wrapping from z to a. If the circular difference is 0, no move is required for that character. Otherwise, we record the difference in a frequency map, which tracks how many times each specific difference occurs. After that, we simulate the moves. For each difference in the frequency map, we calculate the time required for each occurrence using the formula time equals diff plus n1 asterisk 26, where n is the occurrence count. This formula accounts for the spacing of 26 units between repeated uses of the same difference. If at any point the time exceeds k, we return false. Finally, if all differences are satisfied within k moves, we return true. The algorithm relies on several key insights. First, the circular difference formula ensures that we handle the wraparound from z to a correctly, making the calculations seamless regardless of the characters involved. Second, the frequency map provides an efficient way to track how many times each difference is required. This is crucial because it allows us to calculate the time needed for each occurrence without redundant computations. Third, the spacing of 26 units between repeated increments of the same difference ensures that no two increments interfere with each other. This is handled elegantly by our formula for calculating time. Lastly, we use early stopping as an optimization. If at any point a difference requires more than k moves, we terminate the process immediately. This makes the algorithm efficient for edge cases where conversion is impossible. To implement this, we use a frequency map, which is a dictionary structure for fast lookups, and simple integer calculations for differences in time computations. These data structures are both efficient and straightforward, ensuring that the algorithm is clean and performant. Analyzing the complexity, the time complexity of the algorithm is O(n), where n is the length of the strings. This is because we iterate through s and t once to calculate the differences and then process each unique difference in the frequency map. The space complexity is O(1), as the frequency map can have at most 26 entries, one for each possible difference. This constant space usage ensures scalability. Let's also consider some edge cases. If the lengths of s and t differ, we return false immediately without further computation. For cases where k is very large, the algorithm ensures that the spacing by 26 is respected, so it handles these scenarios gracefully. If no moves are needed, such as when s and t are already equal, the algorithm correctly identifies this and returns true. On the other hand, if k is too small to satisfy the required moves, the algorithm accurately detects this and returns false. These considerations make the solution robust and reliable across a wide range of inputs. The provided code solves the LeetCode problem number 1540 can convert string in k moves by determining if string s can be converted into string t within k moves under the problem's constraints. The solution begins by checking if the lengths of s and t are equal. If they are not, conversion is impossible, and the function immediately returns false. Next, a frequency array of size 26 is initialized to 0. This array will track the number of times each shift, modulo 26, is required. The circular nature of the character shifts is handled using modular arithmetic, ord t, I, ord s, I, %26. Each character in s is paired with the corresponding character in t, and the required shift is calculated. If the shift is non-zero, indicating a move is required, it is recorded in the frequency array. The final step is to verify if the shifts can be performed within the allowed k moves. For each possible shift from 1 to 25, the maximum number of times that shift can be used is calculated as k shift //26 plus 1. This accounts for the fact that moves are cyclic and the same shift can be repeated every 26 moves. If the recorded frequency of a shift exceeds the maximum allowed, the function returns false. If all shifts are within the permissible limits, the function returns true, indicating that the string s can be converted to t within k moves. The algorithm is efficient, with a time complexity of O(n), where n is the length of the strings, and a space complexity of O(1), as the frequency array has a fixed size of 26. This makes it well suited for the problem's constraints. In this Java implementation, we start by defining a method named canConvertString which takes three parameters: the original string s, the target string t, and the maximum number of moves k. The first condition we check is whether the lengths of s and t are equal. If they aren't, it's impossible to convert s to t, so we immediately return false. Next, we initialize a frequency array of size 26 to track the number of shifts needed for each character modulo 26. This helps us determine how many times each shift is required. Then, we loop through the strings, comparing each character in s to its counterpart in t. For each pair, we calculate the shift needed to convert the character in s to the one in t. This is done using the formula t.char I, s.char I, plus 26, %26, which ensures the result is always a positive value between 0 and 25. If the shift is greater than 0, we increment its count in the frequency array, since non-zero shifts require moves. Now, we need to verify if it's possible to perform all the required shifts within the given limit of k moves. For this, we iterate through each possible shift value from 1 to 25. For each shift, we calculate the maximum number of times it can be used, which is determined by the formula k_shift/26 plus 1. This accounts for the fact that the same shift can be reused every 26 moves. If the frequency of any shift exceeds this maximum allowed usage, it means the conversion is not possible within k moves, and we return false. If none of the shifts exceed their allowed usage, we return true at the end of the function, indicating that the conversion is achievable within the constraints. To begin solving the problem, let's consider the first example where s equals abc, t equals bcd, and k equals 5. The first step is to check the lengths of s and t. Here, both strings have a length of 3, so we can proceed to the next step. Now, we initialize a frequency array with 26 zeros, one for each possible shift value corresponding to the 26 letters of the alphabet. This array will help us track how many times each shift is required. Next, we calculate the required shifts for each character. For the first pair of characters, s0 equals at nt, 0 equals b, the shift is calculated as ord b ord %26 equals 1. We increment the frequency at index 1. Similarly, for the next pair, s1 equals b and t, 1 equals c, the shift is again 1, so we increment the same index. For s2 equals c and t, 2 equals d, the shift is also 1, so we increment it again. At this point, the frequency array reflects that a shift of 1 is required 3 times, and all other values remain 0. Now that we have the frequency array, the next step is to validate these shifts against the given value of k. For a shift of 1, the maximum number of times it can be applied is calculated as k_shift/26 plus 1. Substituting the values, we get 5 to 1//26 plus 1 equals 1. This means that a shift of 1 can only be used once in the given k moves. However, our frequency array shows that we need this shift 3 times, which exceeds the allowed limit. Because of this, it's impossible to convert s to t within k moves, so the function returns false. Moving on to the second example, with s equals input, t equals output, and k equals 50, the process begins in the same way. The lengths of both strings are equal at 5, so we proceed to initialize the frequency array with 26 zeros again. In the second example, we calculate the required shifts for each character. For the first pair, s0 equals I and t, 0 equals o, the shift is ord o ord I %26 equals 6, so we increment the frequency at index 6. Next, for s1 equals n and t, 1 equals u, the shift is ord u ord n %26 equals 7, so we increment the frequency at index 7. For the next 3 pairs, s2 equals p and t, 2 equals p, s3 equals u and t, 3 equals u, and s4 equals t and t, 4 equals t, no shifts are required because the characters already match, so the frequency array remains unchanged for these indices. After calculating all shifts, we validate them against k. For a shift of 6, the maximum allowed frequency is 50 to 6//26 plus 1 equals 2. Since the frequency for this shift is 1, it's valid. Similarly, for a shift of 7, the maximum allowed is also 2, and the frequency is 1, so it's valid as well. Since all shifts are within the allowed range, the function returns true, indicating that the transformation is possible. In the third example, s equals abc, t equals abc, and k equals 0. Here, the lengths of the strings are equal at 3, so we can proceed. The frequency array is initialized with 26 zeros as before. Next, we calculate the shifts for each character. For all 3 pairs of characters, s0 equals at nt, 0 equals at s1 equals b and t, 1 equals b, and s2 equals c and t, 2 equals c, no shifts are required because the characters already match. The frequency array remains unchanged with all zeros. When we validate the shifts, we find that no shifts are needed, and since k equals 0, this is valid. Therefore, the function returns true, confirming that the transformation is possible without any moves. This concludes the solution walkthrough. demonstrating how the algorithm handles different scenarios. To analyze the time complexity of this solution, we begin by examining the different steps involved. First, checking if the lengths of S and T are unequal requires calculating their lengths. While the comparison itself is O(1), determining the length of the strings takes O(n), where n is the length of the strings. Next, we initialize a frequency array of size 26 to store the count of required shifts. This initialization is a constant time operation, O(1), because the size of the array is fixed. After that, we calculate the shifts required to convert S into T. This step involves iterating through all characters in S and T, performing arithmetic operations like subtraction and modulo for each pair. Since these operations are constant time, the loop overall takes O(n). Thus, the most significant contribution to time complexity so far comes from this loop, which depends linearly on the length of the strings. Next, we validate the shifts by iterating over all possible shift values from 1 to 25. For each shift value, we calculate the maximum number of times the shift can occur within the given constraints of k. This involves simple arithmetic and comparisons, both of which are constant time operations. Because the loop runs a fixed number of iterations, 25 regardless of input size, this step contributes O(1) to the overall time complexity. Combining these steps, the dominant factor remains the loop over S and T, which is O(n). All other operations, including the constant time validation loop, are negligible in comparison. Therefore, the overall time complexity of the solution is O(n). Now let's examine the space complexity of the solution. The main additional memory usage comes from the frequency array, which has a fixed size of 26 to store the counts of each possible shift. Since this array size does not depend on the input size, it requires O(1) space. Besides that, the solution uses a few scalar variables like shift and max_allowed, which also take constant space. The input strings S and T are provided as parameters and do not contribute to additional space usage. As a result, the overall space complexity is O(1), making this solution highly efficient in terms of memory usage. To put this into perspective, let's compare the optimized approach to a naive solution. A naive method might involve simulating the transformation of each character in S into T over k moves. This would require nested loops, one iterating over the characters in S and another iterating up to k shifts for each character. This approach leads to a time complexity of O(n*k), which can become very inefficient for large values of k. In contrast, the optimized solution pre-computes shift frequencies and validates them within the constraints of k, avoiding unnecessary operations. This achieves a much better time complexity of O(n) and space complexity of O(1). The improvement is particularly significant when k is large, as the naive approach scales poorly in such cases. Let's now analyze the time complexity under different scenarios. In the best case, when the strings S and T are identical, no shifts are required. The frequency array remains all zeros, and the validation loop completes in constant time. Thus, the time complexity in this scenario is O(n), as we still need to iterate through the strings to confirm their equality. In the worst case, all characters in S and T might require the maximum number of shifts, and k could be just sufficient to meet the constraints. Even in this scenario, the time complexity remains O(n), as the algorithm processes the strings linearly and performs constant time validation. For the average case, typical inputs will involve a mix of zero and non-zero shifts, but the solution always iterates over the strings and validates shifts in constant time. As a result, the average case time complexity also remains O(n). To mathematically prove the time and space complexity, let's summarize the key steps. For time complexity, the most significant step is iterating through the strings S and T, which takes O(n), as each character is processed once. The validation loop over 25 possible shifts is constant time, contributing O(1). Therefore, the total time complexity is O(n). For space complexity, the only additional memory used is the frequency array, which is of fixed size 26, making the space complexity O(1). No other data structures depend on the input size. In conclusion, this solution is optimal, achieving linear time complexity and constant space complexity by leveraging modular arithmetic and frequency analysis. This makes it a significant improvement over less efficient approaches. When working on this problem, there are several common mistakes you need to watch out for. First, not accounting for character wrapping can lead to incorrect results. For example, if you need to convert Z to A, the shift is not 25 but rather 1, due to the circular nature of the alphabet. Ignoring this wrapping can cause miscalculations. Next, some might forget to consider the move count constraint. Even if a transformation is possible, it might require more moves than the allowed K, which means the solution would still fail. Another frequent oversight is assuming that the strings S and T will always have the same length. Without verifying this upfront, you might begin iterating over the strings, but if their lengths are different, the transformation is immediately impossible. Always validate these conditions before proceeding with any logic. Additionally, another mistake developers make is overlooking frequency collisions in the move steps. For instance, if two characters both require 3 moves to align, you cannot apply the same moves simultaneously. Instead, you need to spread them over different rounds, such as 3, 29, and so on. This can quickly exceed the allowed K if not handled properly. Also, inefficient handling of modulo operations is a common pitfall. Some solutions use nested loops or perform redundant calculations to determine the necessary moves for each character. This unnecessarily increases the time complexity, but the problem can actually be solved in O(n) with better optimization. Avoiding these inefficiencies is key to crafting a robust solution. To succeed in an interview setting, focus on calculating the shift required for each character in S to match T. This can be derived using the formula ord T I ord S I plus 26% 26, where the plus 26 ensures that the result is non-negative. A useful pattern is to utilize a frequency array to track how often each shift value occurs. For example, if the shift value 3 appears multiple times, you'll need to ensure that all transformations fit within the allowed K moves. Optimization is crucial here. Aim to solve the problem with a time complexity of O(n) by avoiding redundant recalculations. During an interview, it's important to communicate your thought process clearly, especially when addressing edge cases like empty strings, unequal lengths, or very large values of K. For further practice, consider problems like LeetCode 848, which involves similar character shifting logic, or LeetCode 535, which emphasizes modular arithmetic and efficient mappings. Other related problems include LeetCode 67, which focuses on modular arithmetic and the logic for handling carry or overflow during binary addition. Another is LeetCode 1638, which examines how strings differ by one character and involves character-level transformations and comparisons. As for alternative approaches, you might consider a brute force method where you increment characters in S1 at a time until they match T. While straightforward, this is highly inefficient with a time complexity of O(n)(k), making it impractical for larger inputs. A better approach is to use a greedy algorithm with a frequency array. By calculating the required shift for each character and tracking the maximum moves needed for any shift, you can solve the problem efficiently in O(n). However, this method does require careful handling of edge cases to ensure correctness. Another option is the simulation approach. Here, you iteratively apply the necessary moves to transform S into T, ensuring that all constraints are respected at every step. While this method is often easier to implement and can be helpful for understanding the problem, it is less efficient than the frequency array approach. The trade-off is that while simulation can provide clarity in smaller cases, it might not scale well for larger inputs due to its iterative nature. Ultimately, the choice of approach depends on the specific requirements and constraints of the problem, but aiming for efficiency and clarity in your solution is always key. Great job! We've just completed LeetCode problem number 1540, can convert string in K moves. To summarize, we used modular arithmetic and efficient move distribution to solve the problem in O(n) time. Remember to practice similar problems to strengthen your understanding. Thanks for watching, and don't forget to like, share, and subscribe to stay updated with more coding challenges. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!